So now we will continue with step 2 of the separating variables method. So the step 2 is satisfying the boundary conditions. Conditions. There you are. What this step says is that we have to determine solutions f and g for f by prime minus k f equals 0 and g double dot c squared kg equals 0, which have already been explained in step 1, how to obtain, so that u equals fg satisfies the boundary conditions. That is, u at x equals 0 is equal to f 0 gt equals 0, and u at l comma t is equal to f at l g at t equals 0. This inequality can be solved if g is always equal to 0. However, this doesn't help because u equal f times g will be equal to 0. And it's of no interest because what this is telling us is that the string will present no fluctuation. So that is not true, so this will not be working for us. Therefore, f at 0 would be equal to 0 and f at l would be equal to 0. That can help because this is not actually telling us that the string will not be fluctuating at different times. Just at this point, it is telling us that it will have no fluctuation. So f equals 0, if considering that f is equal to 0, then k can be negative. That it can be also said to be equal to minus p squared, as we have already mentioned before. Then the equation can be rewritten. It can be write again as f by prime plus p squared times f equals 0, which will be having a general solution equal to f equal to a cosine of a period times x plus v sine of a period times x. That will be a solution of this ordinary differential equation. Therefore, f evaluated at 0 is equal to a, which is also equal to 0, as we need this result to be equal to 0. And f evaluated at L will be equal to v sine of rho L, which will also be equal to 0. This doesn't include the cosine part because we already said that a is equal to 0, so the cosine part will be always equal to 0. And what both equations give us is that period times L is equal to m pi, so that period is equal to m pi over L. Therefore, if we set v equal to 1, we can obtain infinitely many solutions f of x is equal to fn of x, where fn of x is equal to sine n times p over l times x. And we already saw introduction to this result in the step 1 development. Now let's talk about step 3, which is the solution of the entire problem using Fourier series. So to obtain a solution that satisfies both the boundary and initial conditions, we need to consider u depending of x and t equal to an infinite symmetry from n equals 1 to infinity of u and x comma t. That can be also represented as n equals 1 to infinity of b n cosine of lambda n times t plus the n star sine of ln t, that is g of t, times f of x, that is sine of pi n pi over l x, where lambda n is equal to c times m pi over l. We have already mentioned before. So we are just using a Fourier series here that corresponds to the time-dependent part of the fluctuation function u. So this is telling you that Vn is equal to 2 over L. Sorry, no, I'm just skipped some part of the development. So we now need to satisfy the initial condition of displacement. That is u at time 0 is equal to the symmetry of n equals 1 to infinity of Bn sine of n pi over L times x equals to fx that we already mentioned. There is a initial displacement method or fluctuation where x goes from 0 to L. We're only substituting time equals 0 in the whole representation of the fluctuation method as a Fourier series and obtaining it for times equals 0 and making the inequality with it with f of x. So we now know that the coefficient v of n was equal to 2 over L integral from 0 to infinity of f of x multiplied by sine and pi x over L dx. And that is just another formula for the coefficients of a Fourier series that can be analyzed in other videos. And that's how we can obtain the coefficients of the fluctuations function b of n. And so now we can check to satisfy the initial condition of velocity. So we have that the derivative of the fluctuation function at respect of time when time is equal to 0 must be equal to the summatory of n equals to 1 to infinity of minus Vn lambda n sine of lambda n t plus Vn star lambda n cosine of lambda n t multiplied by sine n pi x over lambda. We're just deriving the fluctuation method represented as a Fourier series with respect of time, and this will be equal to the summatory from n equals 1 to infinity of Vn star lambda n sine of n pi x over L. We are just substituting the value of t equals 0, so we only get this part of the representation of the fluctuation method, and this will be equal to g of x, that was the velocity function from the initial time. So this gives us that Vn star times lambda n would be equal to 2 over L, the integral from 0 to infinity to lambda, of g of x times sine of n pi times x over L, derivative of x, and we are just obtaining the new coefficient of the Fourier series there. And finally, since lambda n is equal to c n pi over L, we can just divide this value of lambda n from the coefficients and obtain 2 over c n pi, the integral of 0 to L g of x sine of n pi x over L dx. And we now have yet another coefficient of the Fourier series representation of the fluctuation method function, and that is how we can satisfy both conditions, the boundary and the initial conditions for this string vibration modeling.